Please welcome Patrick Lee of Sempra Infrastructures.
We are here all working towards a clean energy future. There are two global trends that are creating numerous challenges for us today in our journey to a lower carbon future. The first global trend is the rapid adoption of renewable energy such as solar and wind. When and where these resources produce for the grid and how fast they suddenly change is very hard to predict. And the second global trend that affects us is the rapid adoption of distributed energy resources, also known as decentralization of traditional power systems. And it created a coordination problem for us because the timing, the location, the type and sizes of these resources, and their speed of response and their impact to the grid across the network vary significantly. That makes coordination very difficult. So when you combine this intermittency and coordination problem together, it created an even greater challenge for us. And so for smaller grids like an island or like a remote electric grid in a remote area, it becomes a significant challenge for them. Even in pockets of large centralized grid, we're seeing problem of integration where there are significant amount of renewable generation occurring. So there has been a number of innovations to try to solve these problems. For example, there are numerous attempts to do aggregation of resources using the concept of virtual power plants, or the deployment of reactive power equipment to try to address voltage fluctuation problem when we have cloud coverage impacting solar rooftops. However, when we start addressing one problem at a time, it creates problem for another area. And so we really have to pay attention to how we deploy these resources effectively. And so we really have to think about how we can deploy more at a system level. Okay. So to solve this kind of problem, we need to really have a system level kind of thinking. And so a solution needed to be focusing on a comprehensive approach. For example, you can think about a system integration and control solution that can address simultaneously this intermittency and coordination problem all at the same time. So this kind of system level thinking and solution is actually not new. There are actually other industry has adopted a solution like that to address new resources that are hard to address and also very dynamic in terms of changes. So for example, if you look at our military system, we have Army, Navy, Air Force, all have very different levels of sophistication, different speed of response, different impact to the system. So our military was able to, from the old day of Moscow communication to coordinate our troops, to pioneering in GPS-based technology that we enjoy today, by combining with other enabling technology, our military is able to deploy our air, land, and sea resources anywhere in the world, anytime, any place, with maximum effectiveness. And in another industry, like transportation, we have network transportation company like Ubers and Lyft that are able to solve a dynamic resource allocation problem of a system of cars and a system of riders. And they were able to address this dynamic problem using GPS-based technology, as well as other enabling technology like payment settlement process, to now give us the low cost and also high reliability transportation need that we all enjoy. Right? So if you think about this translating into the power sector, we also have GPS-based technology. We also have other enabling technology that can help us solve the intermittency and coordination problem. So if you think about GPS technology, we actually have an invention of GPS-based technology in the power system in the 1980s at Virginia Tech. By combining the physical measurement of voltage and current with the timestamp of a GPS clock, we are able to create a vector called single phasor. So don't be afraid by this big word, single phasor. It's no different than just a vector that you're familiar with. For example, a directional vector that, say, go north 100 miles. The difference between a magnitude measurement that we're using in the power grid today and a vector-based measurement that we will use for control of the power grid now into the future is that a vector gives us more information because along the path of the vector, we have more information to determine how we control the power grid. And so if you enjoy your GPS map, point-by-point direction to tell you how you get from point A to point B, you will enjoy how a vector-based control technology will solve the problem for the power grids. And so in the power grid, the vector, the phasor that we talk about, is actually just a magnitude measurement plus an angle. In an example here, I use, you have 100 volt. What's the reference in terms of angle based on the GPS clock? By having that vector conversion, now we have new information to control the grid at a higher speed and also with higher accuracy. So this kind of technology is really, you think that it's a concept? Well, it's not. It's actually being deployed as a software. By combining GPS-based technology with other enabling technology, such as system modeling, forecasting, optimization algorithm, you can now create a solution to be able to increase the intelligence level of the power grid in control. Let me simplify this into terms that you can relate to. If we think about a hybrid vehicle like a Toyota Prius, it's powered by an engine and a small battery. Certainly, there are innovation in hybrid vehicle technology of the battery application. There's also innovation in the mechanical drive system in a hybrid car. But themselves alone do not produce the overall performance of a hybrid vehicle. It is the smart engine control system that determines the intelligent operating condition of the vehicle to be able to dispatch the battery and dispatch the engine that give us ultimately, at any condition, the higher fuel efficiency and reliability that we enjoy today. So if you draw a parallel to the power grid, we have a GPS-based technology today that we can adopt. And so we have similar functionality that we can achieve in terms of an overall system benefit that we can improve significantly in terms of efficiency and reliability so that we can make renewable integration much more affordable. So let me give you some example where this technology is working today. So this technology has been tested, demonstrated, and deployed in the last 2 years. And the first deployment was as a retrofit solution for an existing wind farm with 24 megawatt generating capacity. And it has an 11 megawatt battery. The original control solution that was implemented some years ago was to use the battery as a shock absorber as the wind condition changes. With this GPS-based technology, we were able to demonstrate that using the battery instead of correcting for the wind condition, to use it to directly address the grid stability problem as a system is much more cost-effective. It makes a lot of sense because when you have battery that are very fast, and then when you add it with intelligent control system, you can respond to these very dynamic quick changes across the network very fast. And the GPS-based capability allow you to do coordination across many devices simultaneously. And so it's very beneficial for this kind of technology. So we also have deployed this technology at a 50 megawatt solar farm and a 200 megawatt solar farm. And most recently, it's been deployed in microgrids as a control solution using this vector-based control technology. Taking the technology even further by adopting best practice in software integration, adopting human-centered design concepts, now we're able to deploy microgrid control solution in just a few weeks. It's a significant transformation from the old technology that we have seen that takes 3 to 6 months to implement. Plus, it's very difficult to make changes with old control technologies. So given all this, what does that mean for a renewable energy future? Well, if you think about these technologies' benefit and the ability for this GPS-based technology to address timing, location of these resources of any mix to benefit the system as a whole, we can now accelerate the adoption of renewable and distributed resources in a significant way. Just imagine renewable energy curtailment could be actions of the past. I think most importantly, when you have a system-level thinking and system-level solution, you're not just addressing the benefit of the renewable that you're adding to the system. You are also trying to improve the existing infrastructure's efficiency so that you can actually bring up existing infrastructure utilization to the maximum, and so as the reliability benefits. So in some of the use cases that we have, we actually have study islands, and when we look at certain islands, when you deploy with a right-size battery, you can actually reduce the diesel generation and fuel requirements significantly. And if we look at economic payback, some of the economic payback is less than 1 year in some cases. So as you can see, when you apply a smarter control solution, it makes a huge difference. We all like to believe that energy storage is the solution of the future. Everyone believes that, right? We can think of battery can solve our renewable integration problem to address intermittency. We can think battery solution can address our grid stability issues. However, not every battery solution is created equal. Think about the example I've given you on the Prius. It's the smart engine control system that made a difference. So when we deploy battery, we need to pay attention to the control system that you're deploying. If you're deploying one battery at a time and not thinking about how they actually work as a system, you're losing the value stack in the battery deployment. So you need to start thinking more from a system level. So if you think about this, a system of 1,000 that you can control, you can also control a system of 1. But it doesn't work the other way around. So with a GPS-based advanced control technology like this exists today to address our integration and distributed energy resource problem, we can overcome the intermittency and coordination problem. Our path to a low-carbon future can be much accelerated. So in reality, our renewable future is much quicker than you think. Thank you.